Good morning. So let's start. This is the 17th lecture on computer control, and it's about stochastic control. Stochastic control is perhaps a very heavy word. What we want to do is to control plants, linear plants, described by a transfer function, or by equivalently by a difference equation that are excited by some steady state random signal. An example is, for instance, an aircraft in which you want to keep the attitude, and it's disturbed by a wind that exerts random force on the aircraft. Another example is the production of paper, in which you want to keep the thickness of the paper measured, say, in units of mass per square meter. When you go to the shop, you ask for paper with say 80 grams per square meter or something like that, and you want to keep it close to this set point. So we describe the plant and the disturbance using the so-called Armax model. So the Armax model is shown in this slide, and it's A, B, and C are polynomials. I'm assuming that the delay is 1, or it's at least 1. So the delay is D. In many cases, we will be assuming a nominal delay of D of 1, but things work for bigger delays. But the important thing is that the delay given by the difference of the degrees of A and B is positive, so that the system is causal, and it is at least 1. And I'm assuming that the degrees of polynomial A and polynomial C are n. So this is a misprint. This should be degree of C instead of the degree of B. Okay, so degree of B is lower than the degree of A because of this condition on the delay. And furthermore, at this point, for this type of method, we assume that the polynomial B has all its roots inside unit circle. That is to say, all the zeros are minimum phase or are inside unit circle. This means that the system has an unstable, as a stable inverse. I mean, if you consider A divided by B, which is the inverse system, apart from causality considerations, it is stable. It is asymptotically stable because of this assumption. Of course, this is a limitation. There are important classes of plants that for which this is not valid. We will later alleviate this constraint. So assume that you are, I will call in these slides t, the discrete time as t. Okay, so assume that you are at time t, and you want to select your manipulated variable u of t. Okay, that's your problem. And your computer is at time t, that's present time, and the computer should run an algorithm to compute u of t. Now, we formulate this problem as an optimization problem. So we are going to find u of t such that the expected value of the square of the output at time t plus d is the least possible one. No. Actually, this expected value is the expected value given the observations up to time t. Okay? So you do this because you want your control variable to depend on data up to time t. So this is a conditional probability. And why is this? Well, if you want to drive the output of the system to 0, why should you do it? Remember, linear systems are obtained by linearizing nonlinear systems about an operating point. So you have an operating point and you want to keep your operation close to that operating point, usually an equilibrium point. So driving the output to 0 is driving your full output to the operating point. That's why we do this. And this is nothing more than the conditioned variance of the output. So it's a power of the fluctuations. You want to have fluctuations around 0, that is to say around the operating point, of the least possible value. Why consider the variance or the power, the variance is the same as the power, at time t plus d? Now, your system has a delay d. That's the difference between the delays of A and B. And so if you are at time t and you take a decision about your control variable at time t, the first time instant in which you are able to influence the system is after the delay, which is at time t plus d. So I could have replaced this functional by instead of d having something which is bigger than the delay of the system. Okay, but I'm assuming that I will try to drive the output of the system to value which is as close to 0 as possible in the least possible interval of time. Okay, it's interesting to see when these ideas came out. You see two names here, Carl Ostrom and Vladimir Peterka. Carl Ostrom, he was a Swede, and he was in '62. He was a little bit older than you are. He invented these things and made some other important contributions to control. And he was working at the IBM Research Center in Sweden, in Stockholm, I think. And in Sweden, you have large forests. So pulp production, so the production of the raw material for paper, if you think pulp is a kind of, it's like paper. I don't know if you ever have seen pulp, but pulp is like, imagine a thick paper that you can use later to produce paper itself. And paper production was quite important in Sweden at that time. So he was considering the problem of producing pulp with the smallest possible fluctuations in the thickness. Okay, and he invented this control law, the minimum variance control law. Okay, so the minimum variance, why? Because you are minimizing the variance of the output. Remember, it's the conditioned variance. It's not a steady state variance. And Vladimir Peterka was the other side of the Iron Curtain. And he was a member of the Academy of Sciences of Czechoslovakia, which is a country that no longer exists. It has been split into to the Czech Republic and Slovakian Republic. And he was also concerned with problems mainly in steel production. Okay, Czechoslovakia was known for instance, for shotguns in the factory of Brno. But in general, steel was quite important in the Czechoslovakian Republic. And Peterka invented also minimum variance control in an independent way of Carl Ostrom. And it's nice because they both rely on input-output models. If you travel the Atlantic and go to the United States, the description of the plants were not based on input-output models. They were based on the state space model. Why? Because their concern was about space exploration, going to the moon, putting satellites in orbit. Okay? And this had to do with socio-economic conditions, because Europe had just came from a very terrible war, the Second World War, that destroyed everything in Europe. So the concern was to produce paper, to produce glass, to produce steel, to reconstruct society. Instead, in the United States, this was not a problem. The problem was a problem of political affirmation, so going to space, okay? So that's why in Europe, algorithms tend to be based on input-output models, because if you are considering the production of steel, it's difficult to measure the state, but you can measure the output of the plant. Same for paper, same for glass. But if you are considering space problems, then the state is quite natural. It's the position and velocity of all independent moving particles. So you have this interplay between social effects and the economy effects and the type of science that you do. Okay, so this is about almost 60 years ago. It's invented almost 60 years ago. So how can we do it? So we have, remember, we have the Armax model, and we want to use the Armax model to find the control law that minimizes this so-called minimum variance functional. Okay, let me tell you a little bit about the relation between quality and control that is made through this control objective. Suppose that you are producing something like paper, okay? So when you say, I'm producing paper of 80 grams per square meter, you are not producing always paper of 80 grams per square meter, but sometimes you are a little bit below and sometimes you are a little bit above. So this straight line, this horizontal line, is the thickness of the paper, okay? So point A corresponds to 80 grams per square meter. But if you do some statistics, then if you build an histogram, okay, with some probability, you will be a little bit below or a little bit above, and with some fluctuations. Now, if you do a contract to produce paper of 80 grams per square meter, when you do the contract, you don't say just, I'm going to produce always paper of 80 grams per square meter. You are going to say 90%, when this is just a number, for example, 90% of the times I will be producing at least 80 grams. Okay, so the set point A for your process is not at 80 grams, but it's above 80 grams. Okay? And it is such that the area under this probability density function, think of it as an histogram, is 90%. Okay? And you are violating only the yellow part, okay, which is 10%. So the worse your technology, the higher you will have to produce. You have to settle your set point. Okay. Now, if you improve your control system, fluctuations will be smaller. So by still ensuring that you are producing paper 90% of the time with your specifications, you can lower the set point, okay, to point B. and still the yellow part is 10%. But now, since you are concentrated at a lower value, okay, in Portuguese we have an expression, a slang expression, which is o coeficiente de cagaço é melhor, okay? So you can reduce your set point, okay, because you are confident that the fluctuations are smaller, so you will be respecting your contract and ensure that only 10% are out of order, and you are saving a lot of raw material, okay? So by reducing the variance of your output, you are actually gaining a lot of money. Okay? So there is a relationship between the money that you are making with your process, because you are using, in average, less raw material, and furthermore, even more important, quality means that your product is always the same. I mean, if you are making pencils, if you sometimes produce a big roller ball, or sometimes there comes Mont Blanc, that's poor quality. I mean, if you are producing big, you should also always produce big. Okay, if you are producing Mont Blanc, you should always produce Mont Blanc. Okay, imagine what was the idea of someone, how would someone would consider things if they buy a Mont Blanc and then when they open the package they find a big. Okay, so quality is associated to uniformity in production. Think about the car industry. In the car industry, things, the different parts of a car, for instance, the door and the chassis, should be in agreement, their dimensions. They have very tight specifications for the fluctuations of the value of the size of a door, because it should perfectly close. If sometimes you produce doors that are a little bit bigger than they should or smaller than they should, then the quality of closing your door will not be the same, and the quality of your car will not be the same. Even if you are producing plastic parts that must be put together, you have very tight specifications. So quality is associated with producing always the same thing, as closest as possible to the reference that you can. Okay, this is achieved by control. So minimizing the minimum variance functional, in this case, has a very tight relationship with production, the quality of production, and the money that you produce out of your factory. Okay, now how can we do it? Let's enter the technicalities of designing minimum variance control. Now, instead of working with a forward shift operator, what shall I do? I shall multiply remember my model. My model was this, okay? So I'm multiplying this by Q minus N, and I get, when I multiply Q minus N by AQ, I get the reciprocal polynomial of A, which is now in Q minus 1. Here, I get the reciprocal polynomial of B and the extra power of Q, which is the delay. That's the difference of degrees of B and A. And C has the same degree of A, so I get here the reciprocal of C. So I get this model here, okay? This model here. And this the delay of my system. So what shall I do? Remember the magic formula of the division of polynomials, C divided by A. This was associated to prediction. We saw it yesterday. So I do this division, up to degree n minus 1. So my quotient, fd, has degree d minus 1. You see, fd, I wrote it here, and it has degree d minus 1 because this is minus d minus 1, okay, between parentheses. And then the remainder is q minus d gd. gd reciprocal at computed for the delay operator. Okay. Now, this is just a formula. Okay. This is just a formula. Although it's a formula that makes us remember about the story of prediction. But if you don't remember the story of prediction, just consider the formula. Okay. And if you multiply everything by a, you find that AF is equal to C minus Q minus DG. Okay, I'm omitting the stars and the arguments. Okay, so I think that these two expressions are equivalent. This is an obvious fact, just algebra. So what shall I do? What shall I do is I'm going to multiply all my model by F. Okay, so I pick up my model and I'm multiplying everything by F. FA, FB, FC. So it's written here, the next slide. AF, Y of t plus D, BF, U of t, CF, E of t plus D. Okay. Now, why do I have here U of t and I have here Y of t plus D and D of t plus D? That's because when I multiply everything by Q minus D to get the delay, or Q minus the degree of A to get the backward representation, this one that you see here, you have already the delay, okay, appears, okay, UT and YT plus D, that's the effect of the delay, the plant delay. Now, so I have multiplied my model by F. Now, I use the fact that AF is C minus Q minus DG, okay? This is just the division, the formula that comes from the division of polynomials C and A. So I replace AF by C minus Q minus DGD, and I get this stuff here, okay? This other formula. Now, what does it tell you? It tells you that C star Y of t plus D minus, then we have Q minus D and GD, but Q minus D applied to Y of t plus D is YT. So this second term is nothing more than GD Y of t with a minus sign. So I put it to the other side and then I divide by C and I get this formula here. Okay? So this kind of this formula is what? It's a prediction formula. It tells you that Y of t plus D is what? Is, okay, imagine that this is 1, that C star is 1. So your noise is white. Okay? It's a linear combination of Y. It's a linear combination of U and a linear combination of future noise samples that detect on the system. Okay? So everything up to here, to this plus signal, depends on t or the past. This is noise that appears on time t plus 1 in its future. Why t plus 1 in the future? Because we have E of t plus D, and remember that FD is 1 plus F1 Q minus 1, F2 Q minus 2, etc. And it has a degree which is D minus 1. So this is a linear combination of ET plus D down to ET plus 1. And the coefficients of the linear combination are the coefficients of this F polynomial. So this first part depends on data up to time t, and this first second part depends on data up from time t plus 1 in the future. So they are independent. Okay, they are independent. Now, if C star is not 1, but it's some polynomial, then think my conclusions are not affected because this is just a filtering of past data. Okay, and this C star does not affect this term. Okay, remember that when I divide by C star, that C star cancels. So you get FT star. Okay, so I could write my y of t plus d as a sum of two terms. And I've placed these two terms between these squares. This term depends on variables up to time t and also on ut, which is the control value that you want to compute. And this term that I call beta, so I call the first one alpha, and I put alpha of ut because it depends on ut. And this second term, beta, depends on variables that appear only after from t plus 1 up to t plus d, so in the future. Okay, so my y of t plus d is in this can be written in this form, and I know that alpha and beta are independent because this is the past and this is the future. Okay, when I think this as a function of v. Now let's pick up your model and plug it in the functional that you want to compute. So you replace y by alpha plus beta, that's here. And then you develop the square and take the expected value. Now, you have the expected value of alpha square, the expected value of beta square, and then the expected value of the product of alpha beta. But since alpha and beta are independent from each other, then the expected value is the expected value of alpha times the expected value of beta, and they are both 0. Okay, so there is no cross term here. Okay, so now look at this first expected value. It's the expected value of terms that depend on variables up to t, given all the information on y and u up to t. Okay? So the expected value of one thing given that thing is the thing itself. So the expected value of x given that x equal to 5 is nothing more than 5. So I can take out the expected value from the first part. The second part, the second parcel, I'm taking the expected value of a quantity that is conditioned on variables that are independent on it. So this conditioning does not affect the expected value. So I can just take out this given observations up to time t. Okay, so I can write my functional in this way. So let's remember what is alpha and beta again. Clearly, the smallest value for j, since this second term does not depend on u, is by making alpha equal to 0, because if alpha is a linear function of u, the smallest value of alpha squared with respect to u is when alpha is 0. So I just remember what is alpha. Let's recall what is alpha. Okay, alpha is 1 over c g b, or if you multiply everything by c, it's g dy plus b star f star u equal to 0. Okay, So you have this, the optimal control verifies this expression here. And if you solve it with respect to U, this VM means that's the minimum variance control, verifies this equation. So U is nothing more than filtering the output by G divided by dF. Okay. Now, if you multiply by Q minus N plus 1 above and below, you can show that this can be written actually in terms of the forward shift polynomials. Okay, so you can write the control law in any of these forms. Okay, so with this minimum variance control, you are annihilating this alpha squared term, and your variance is the smallest value of your variance is the expected value of beta. But beta, remember, what is beta? Let's go back. Beta is a linear combination of future values of E multiplied by the coefficients of F. Now, if you take the square and then the expected value, all the cross-coupling terms, say E of t plus 1, E and D of t plus 2, or E of t plus 4 and E of t plus 1, they are all 0 when you take the expectations. And the only thing that remains is the variance of E. So E1 squared, E2 squared, E3 squared, and so on, multiply by squares of F. So you can place your sigma E squared in evidence, and this expected value of beta squared is the sum of the squares of the coefficients of the F polynomial multiplied by the variance of, which is a number, the variance of the noise. Okay, so I don't have a slide with the conclusion, but the conclusion is in these two slides. The minimum variance control law, what should we do? We should do this division of polynomials to find F and G. G defines the controller. F has influence on computing the best possible value of the performance of the controller, so the minimum attained variance of the output. I find, after I have G and F, I compute, this filter is my controller. Okay, can be written in the backward shift operator or in the forward shift operator. And what is the best thing that I can have? The best thing of my variance, of my closed loop variance, is given by the sum of the squares of the coefficients of polynomial F times the variance of the noise. Any question? Let's see one example. Suppose that we have this plant in which A, B, and C are these polynomials, and we have a delay of 1. Okay, and assume also that the variance of the noise is 1, and we want to find the minimum variance control. So what shall we do? I was lazy. I don't have the computations, but what I do is I divide C by A. In this case, F is just one constant, which is 1. And then I use nothing than this formula here. Okay. Now, suppose that you make U equal to 0. If you make U equal to 0, your plant is 3. Okay, so your output is just wandering. If you repeat it with a different sequence of noise, you will get a different sequence of the noise of outputs. But you see the scale here between 0 and 90 after 100 steps. You can actually remember, you have learned how to compute the variance of the output of this linear plant. So it's a linear plant with 0 input. Okay, the excitation comes from the noise. Now, okay, let's compute the minimum variance controller. So this is C and this is A. Sorry, this is C and this is A. So I'm computing C divided by A. And I stop at the first term. So this is my F. And so I select, how do I select this coefficient? It is such that multiplied by this first coefficient will cancel out the first coefficient of this polynomial when you subtract things. So it's clearly a 1, so I multiply everything by 1, so I repeat this polynomial here, and I subtract, I cancel the first term. And I stop because the delay of the plant is 1, so my F is of order 0, that's a constant. And here I have Q minus 1, G1. So G1 star is 3.2 plus 0.2 Q minus 1. And my F star, F1 star is just 1. Okay? And my minimum variance controller is 3.2 plus 0.2 Q minus 1, 1 plus 0.5 Q minus 1, like that. Okay? Now, let's see a simulation of the result. Remember, in open loop, you could see the signal going up to 90 almost, probably even bigger values. But here, what you see, it fluctuates. Y is fluctuating here. U is also fluctuating but not growing, and they are in steady state, you see. And this is between -4 and +4. Now, we know that the variance of the output is the square of the coefficients of F, which is just 1, multiplied by the power of the noise, which I told you it's just 1. So the variance of the output is 1, and the standard deviation of the output is just take the square root. The square root of 1 is 1. So the standard deviation of the output is 1. If you assume that the output is between plus or minus 3 standard deviations, you are expecting most of the values of y to be between -3 and +3. And if you look at this graph, this is true. Okay. The other important thing is that u is not growing up. So things are okay in this example. Now, another way of looking at things is by making histograms. Okay. Remember that there is probably a small, in the first samples, there is a small transit that you can even not notice. But after, say, 30 points, it's in steady state. So you can build the histogram, so that the histogram is you divide the values of y in boxes. I do this for the open loop case between -2000 and +2000, and I have, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes. So I have 10 boxes between -2000 and 1000. And I count the number of values within these boxes. So I build the histogram, and I have this distribution. Okay. Now I do the same for the control system, and you see that this is here. You have values between -2000 and 1000. Here you have values between -3 and 3. You see. So you can look at histograms to control the quality of your system. You can ask, well, what about if I don't have a minimum variance controller? I just place the controller there. Okay, you can compute the minimum variance control. You can plot the histograms, and you can evaluate your controller. Actually, there are techniques for that do not need to explicitly compute the minimum variance controller, but that's another story. So this is an important thing. You are at a factory, and you want to see, is my controller good enough? Okay, am I close to open loop or to the minimum variance control? Okay, and you can plot these histograms to evaluate that. Any question? No questions at all. Okay.
Professor, I have a question.
See?
Just really quick. It's about the controller. This
Uh-huh.
controller is could you say this control is optimal for linear states in regarding the output being 0 or the estimate of the output?
Okay, that is a good question. So your question, I think, is if you compare you have studied the LQ controller that you are using in the lab, and then you have this stuff here.
Yes.
Okay, so in one side you have all that stuff of the Riccati equation.
Yep.
And here you have a division of polynomials. Okay.
Mm-hmm.
What is your hint? What is your opinion? What is your feeling about this? Is this the same thing or not?
Regarding,
let's look at the cost function.
I think it's this. I think it's optimal, yeah, because of the cost function. I don't know. Maybe yes, maybe not.
Actually, no. And
no? Okay.
What is the big problem? Okay, that is a very good question. And when people invented this, they were puzzled because they said, well, for years we have been studying this story of the LQ control. Actually, LQ control appeared more or less at the same time, in the end of the 50s. Okay. But this is much more practical because we just divide the polynomials and that's it. We don't need any particular numerical methods to solve Riccati equations. Okay? Now, what is the problem? The problem is that in the other case, the control law that you are using in the lab, you are considering an infinite horizon. Okay, so that minimizes the power of your output. You always refer to the state. So remember that you can write y as cx. So you can write this instead of having y squared, you write x transposed c transpose c, which is a matrix, times c times x. But that's immaterial. Okay, that is immaterial. The fact that here we have the output variable, and in your case, in the other case, we have a state, it's immaterial. Okay, the big difference comes from the fact that in the LQ controller, in the linear quadratic controller, you are considering an infinite horizon. Okay, and I told you that in the infinite horizon, the resulting controller stabilizes your system. Okay. Now here you just have this story of the conditioner. That's the key, because you are just considering one sample in the future, and that's the first sample. You see? So in minimum variance control, you are just saying, well, my output is minimum at the first time I can affect it, but later on I don't know what happens. I have no concern. In the case of LQ control, I'm considering an infinite horizon controller. Okay? And with LQ control, in particular, you have insurance of stabilizing your system. Here, this is not the case. I will show you in a moment a situation in which you are not able to stabilize the system. Okay. So things are actually not the same, and you cannot replace solving a Riccati equation by just dividing to polynomials. Okay, that is a very, very good point, and this is quite an important issue, in particular when we think about. I'm not sure whether we are going to have time to discuss that. Maybe not, because of all these holidays and bridges between holidays. I don't know. I really don't know. Usually, you should have 26 classes. I think that this year we are going to have 17 classes or maybe 19 classes. That's a tremendous thing. But I can mention to you, if you try to solve adaptive control you put together online identification and control. So you are identifying your system whenever you receive new data online. Okay, instead of having a batch of data obtained from experiments, you get a model and then you design a controller. No, you get one more point, you update your model, and you recalculate your control law. That's adaptive control. And if you consider that for nonlinear plants, even for linear plants, but in particular for nonlinear plants, now people speak a lot about connections with artificial intelligence, the story of reinforcement learning. And in the reinforcement learning, what you do, you decide your control value according to the reward. The reward is a cost. Okay, the guys from artificial intelligence, they maximize the reward. We control engineers minimize the cost. Okay, but that's just the question of multiplying by a minus sign. That does not change anything. Now, what is a good cost? Okay, a good cost should be something that keeps your system in order up to the end of the times. So in an infinite horizon. Okay. And if you do it just in one step, things went wrong. Okay. There is a famous example in 1965. It was a very unfortunate example. In the United States, they developed an experimental airplane, jet airplane. It was the X-15. It was the rocket airplane. Okay, and they used adaptive control. And what was the controller? The controller was something that was adjusting a gain, just one proportional gain. And the adjustment was according to a gradient rule, depending on something which was not this minimum variance functional, but it was something they did not even have a model. So it was even simpler, but the idea was just consider this cost in just one point, okay? And there was a big disaster. The pilot died, okay? For many years for instance, in MIT, adaptive control was something that was forbidden. No one was studying adaptive control. Now we understand a lot of things in theoretical terms, for instance, conditions for stability that allow you to be confident that things work. But the key point is that if you use functional based on just one step, then you can have problems, okay? Then you can have problems. You can solve some interesting examples, but you have this condition. Remember, I said polynomial B has all its rules inside the unit circle. If polynomial B has some roots outside the unit circle, then boom, it does not work. Okay, it does not work. Let me give you one example. Okay, let me give you one example. Suppose that this is your system, first order system, very simple. Okay, it's stable. It's stable. No, sorry, this is a second order system. So it's A is here, second order system, but it's open loop stable. But the B is 0.9 Q plus 1, and it has a 0 at minus 1.11111. Okay, minus 1.11, which is outside unit circle. Okay, so this is non-minimum phase. And you compute your controller, and then you do an experiment, and you see that Y is apparently it's working. You see, between -3 and 3, okay, this is well controlled. But look at U. U is exploding. Okay, there is an internal mode which is unstable. Now, if you solve the same problem with your infinite horizon LQ controller, this would not happen. Okay, Andre, was Andre that did the question?
Yeah, I'm listening, Professor.
Okay.
It makes sense, yeah.
Could this answer your question?
Yeah, it answered perfectly. Thank you.
Okay. More questions. So one important thing, we have two important things to here. One is from, say, a theoretical point of view. We have a controller, and what happens to the closed loop poles of the controller? Where do they go? That is one thing. The other thing is, how can we overcome these problems? Okay. This type of algorithm, you can say, well, forget about minimum variance, use linear quadratic control. We could have a linear quadratic controller based on stochastic models. Okay, actually it appears like that. But we are going to follow another road. We are going to follow another road that leads to, that exploits the good parts of these things and avoids the problems. So let's go to the first question. So we have two questions. What happens to the poles when you apply minimum variance control? What are the closed loop poles? Let's look at this question. The other question is, how can I modify this law to avoid this instability effects? Okay, so let's look at the poles. So we have this magic formula. I call it a magic formula, but it's just the division of polynomials formula. Okay, I multiply everything by A as I did before. And now I multiply everything by Q up to N plus D minus 1, and I use the definition of a reciprocal polynomial, and I end up with this. I mean, you must think a little bit. Remember that Q up to N, multiplying A star gives you A of Q. And the Q of D minus 1, remember that F is of degree D minus 1, gives you F, okay? Now here, this is of order N, so Qn gives you C, and then you still have Q up to D minus 1, that's why it appears here, and so on, okay? So within the square, you have the formula for the division of polynomials, but disguised, okay? Manipulating in this way. Okay, remember this formula. You know it by heart? I've written it here. Now, it's not written here, but it will appear. We should look not just at the output, but also at the input. Okay, so it's quite important that we always look at the input. Remember the example I gave you? The output was well controlled, but the input was unstable. It was a signal going to infinity. So let's treat our system as a system with one external input, which is the noise, and two outputs, y and u. So to get the equations, this is a kind of one input, two outputs. It's a multivariable system, a simple multivariable system. So I write on the first line of this matrix equation, I write just the equations of the system. So ay minus bu equals to ce. That's nothing more than the model of the system. Now, on the second line, I write the equation of the controller, of the minimum variance controller. Okay, so remember that the minimum variance controller, where was it? Could be written in this way: u equal to minus g divided by f bf. Why? So you multiply bf by u and g by y, and then you have this minus. You can write u plus this stuff equal to 0. Okay, that's the second line that you have here. Okay. Now, and remember that these are transfer functions. So if you consider the if you consider a transfer function associated to this model, what you have to invert this matrix, and to invert this matrix, the denominator, you have something divided by the determinant of the matrix. Okay, and the determinant gives you the poles. Okay, so you compute this determinant. This determinant will give you the poles of this system. When you compute actually now it's a matrix transfer function. Now this determinant is what? Is AFB plus BG. So you can put the B in evidence. Okay, so this gives you all the poles of the closed loop system. Now, you can use the formula for the division. Remember that we came to the conclusion that AF plus G is QD minus 1C. So you can place it here, and you get this yellow expression. That's the characteristic equation of the, sorry, my eyes, of the closed loop. So the roots of this equation, the roots in Q of this equation, think of Q as Z, as a variable, gives you the poles, the closed loop poles. Where do you have poles? You have poles at roots of C. Okay, this is not a problem because we have assumed that all the roots of C are inside unit circle. We have poles at roots of B. Now, B must be inside. B must have all its roots inside unit circle. Otherwise, you are placing a pole, since you are canceling all the zeros, you are placing a pole outside unit circle. Okay, you see? That's the reason why we ask all the roots of B to be inside unit circle, because otherwise we would have closed loop poles outside unit circle. We have an unstable mode. And due to this pole zero cancellation, the output is okay, but the input is not okay. And then you have all the poles the remaining poles at the origin. Okay. Now, some of you, I don't know whether you have studied linear quadratic problem, the infinite horizon linear quadratic problem in CE. Some of you have followed the course on control on espaço de estados. But if you haven't, let me tell you where are the position of the poles when you consider LQ control. in relation to B, okay, this is a particular situation in which, look, let's look at the functional. Sorry. In the LQ control, we have an X return, which is an R times U squared, which is not here. Okay? This is one reason for the trouble. Because in that term, weight, if U starts to grow, then uh, the J fills it. Okay, and the control law with a weight on U is regularized. Okay, not here. That solves part of the problems, as we are going to see, but not all the problems. Okay, but not all the problems. Now, suppose that R is very small. Where do LQ control places the poles? It's very clever, because if the zeros of the open loop system are inside the unit circle, they cancel the zeros as this control minimum variance control does. But if the zeros are outside unit circle, then they mirror the position of the zero with respect to the unit circle, and they place the poles at the mirror. So the poles are always inside the unit circle, okay, with LQ control. That is to say, if you have a pole if you have, sorry, a zero, a point zero, and with in a position with a radius, say 5, and some angle theta, the pole will be at position 1/5, that is 0.2, and position minus theta, that's mirroring in this sense. So minimum variance control cancels all the zeros. If we have a zero outside the unit circle, disaster, okay? It's, you have an internal instability. But with LQ control, if you have a zero outside unit circle, the pole will be placed not over the zero, but in the mirror of the zero, which is inside unit circle. Okay, that's the advantage. Any question? Okay, so where do poles go? Now, I mentioned to you, well, in LQ, we have a term which is penalizes the input. So why not to modify this to penalize this stuff, okay? And it's a very simple idea. It took about 10 years. So it's about 72 or something like that. That two other guys called Peter Graustrop and David Clark. David Clark was a professor at Oxford University. And Peter Graustrop, who is still active, is an old man. I think he has retired. But every now and then he published something, still published something. And he was a student, a PhD student at the time. So they have this idea about 72 or 73 to add here a weight to modify this cost. Okay, so let's see. Okay, so the idea was to put here, let's call it raw weight, and then you have this term. Okay, I wrote here 74 because that's when they published the paper. But of course, paper takes about 2 years, so the idea is should be about 72. And how can we solve this? How can we solve this? let me give you one idea, and you see here predictive control. I will mention this in a moment. Later we can do some exercises, and you can look at solved exercises in previous tests. You have several examples. Now, when you have that stuff of computing the prediction, actually you are expressing, suppose that we have a delay of 1. Okay, let's assume that the delay of my plant is 1. So I can write y of t plus 1 is some coefficient ut plus a linear combination. This s is a linear combination of past values of y up to time t and u from time t minus 1 backwards. And you have, of course, e of t plus 1. Okay, so this formula here is nothing more. Let's go back to the beginning of the class. Suppose that C is 1, so cancel this out. Okay. Now d is 1, so y of t plus 1 is, this is a linear combination of past values of y. Then you have the first of this is ut. I'm individuating because ut is free. And then you have a linear combination of past values of u. So ut minus 1, ut minus 2, etc. Okay, and then d is 1, so this is just one constant, which is 1, e t plus 1. Okay, so you can write it, you can write that formula in this way. Okay, pick up your cost and place your cost there. And remember that these first two terms are orthogonal to the last one. So when you compute the expected value of the square, okay, there is a term here which is orthogonal to the other. So the cross term is 0. Okay, so if you compute the expected value of this square, you have the expected value of these first two, the sum of these two, okay, plus the expected value of this one, plus the cross term, which is 0, and plus this other term. Now, you use the usual argument in relation to which these two terms and that term are known at time t, so the expected value of them given information up to time t are just those terms. And the expected value of these two terms, of this term squared, since given the observations up to time t, these observations are orthogonal, are independent from e of t plus 1, so you can just take the expected value. Okay? And actually you can, in this case, this is just 1, that's it. Now, this is your alpha, okay? You want to minimize this term with respect to ut, but ut appears here, it appears here. Okay, you cannot just equate it to 0 because this is a square plus another term which is squared. So you have to differentiate it with respect to ut equated to 0. So when I write this, remember, I'm not differentiating it with respect to the function ut, is to the value ut of the sequence u, of the function u. Okay, so this is a normal, ordinary derivative. Okay, let's compute it. If you compute it, you get this stuff, and you solve it, you equate it to 0, you get the optimal control. Okay, and the optimal control is very funny because ut is minus, and this is a gain that multiplies, a vector gain that multiplies, this s is a past is remember, S contains the past values of Y and the past values of U. If the plant is second order, contains YT minus 1, and UT minus 1, for instance. And so this is very much similar to the LQ control. It's a kind of, instead of having a state, we have, actually it's a state, but it's a non-minimum state, because we have, say, 3 variables for a second order plant. But it's a feedback, and this is the vector of the feedback. Suppose that rho is 0. If rho is 0, this term is not here, minimum variance control. In minimum variance control, what do you get? Rho is 0, so you have minus W1 divided by W1 squared. That's 1 minus 1 divided by W1. Okay, so pi 1 transpose divided by W1. That's exactly minimum variance control. Okay, when rho increases, you are changing the gains, and you are changing the position of the poles, and so we call this detuned minimum variance. Okay, so one approach by playing with this rho, you can stabilize non-minimum phase plants. It happens that you can still find plants that are not stabilizable by this control law. For instance, there are open loop plants that are in open loop, both non-minimum phase and unstable. In those cases, this control law does not stabilize them. Okay? So what was the idea? The idea was that instead of having just one point at time t plus d, consider several points between t plus d and t plus d plus something, some horizon. Okay, that's the idea of predictive control. If we have the opportunity, I will give you a lecture on this predictive control. Questions? Let me sum up what we have learned today. We started with a plant with stochastic disturbances. Okay, and what have we done? We said, okay, let's you define a control function that we want to optimize to find out the control, which is the variance of the output at a time in the future, which is the present time plus the plant delay. Okay, that's minimum variance control. And by using the formula for the division of polynomials, we obtained the control law. Now, we computed the closed loop poles, and we came to the conclusion that if the plant has zeros outside unit circle, you are canceling those zeros, and you get an unstable, internally unstable closed loop, which is a very bad thing. Now, the other idea was, okay, let's penalize the values of the manipulated variable to prevent them from growing. And we have the tuned minimum variance. And in this way, I'm still able to stabilize non-minimum phase plants, because I'm penalizing the input, and I no longer cancel the zeros. The poles are in other positions. And this was a very good idea. The first practical applications, in particular in adaptive control, they use this type of detuned minimum variance control. And but they are still not yet able to stabilize open loop unstable and non-minimum phase plants, both things. Now, the next step will be, okay, we have the control law based on an infinite horizon. Why not to extend here the values, instead of having just one step, having y squared t plus d plus 1, y squared of t plus d plus 2, and so on, up to some horizon. Okay? That's the idea. So trying to approximate an horizon that is large enough so that it approximates the infinite horizon. Okay? And this is the idea of predictive control that we have not studied. Maybe you say, but why to have all this trouble and not just using the beautiful formulas for LQ control? Well, when you formulate your controller as the minimization of a cost that you are explicitly minimizing, then you can start imposing a number of constraints. For instance, the rate of change of temperature must be smaller than something, or the manipulated variable must be smaller than something. Okay, so you can add constraints. With LQ, the formulas for LQ control, you cannot do this. You can do some, you can play with the weights, but you cannot solve. It's very easy to find constraints that you cannot impose. With these techniques, you can impose them. So they are very, very powerful. This is perhaps the most powerful family of techniques that has ever been built. And it's on the realm of predictive control. And I hope that we had still at least one lecture so that I can tell you a little bit about predictive control. Okay, final question?
Professor, regarding what you've said before about the next week's the holidays and the pontes, will we have class on Monday as well or not?
In principle, yes. I asked Professor Pedro Lima and he said, well, I asked him yesterday, and he told, well, the Conselho de Gestão is going to have to yield a decision. And they should have published the decision yesterday. So up to now, the only thing I know is that there is what we call in Portuguese tolerância de ponto. Tolerância de ponto does not prevent me to present a lecture. Okay. Actually, unless they tell me you are not allowed to give the lecture on Monday, next Monday, I will give the lecture. If this happens, I will. If I'm not allowed to give the lecture, if I receive an explicit order from Conselho de Gestão not to present lectures, which would be quite strange, but it's possible, I will send you an email so that you don't have to connect and be expecting that I connect and so on. Okay?
Okay, thank you.
Any other question? So I will continue with my saga of reviewing the tests. And for you, I hope you have a good day and study a lot. Bye-bye.
Thank you.